The basic premise of my project is carbon dioxide capture and conversion to hydrocarbons, which can be used as a cleaner fuel alternative. This is a two-step process. Carbon dioxide first has to be converted to carbon monoxide before it can be converted to hydrocarbons, and my project is mainly concerned with this first step. In the equation CO2 to CO, one oxygen molecule is taken out, and this oxygen molecule needs to be put somewhere. The perfect place for it to be put is a perovskite for two reasons. One, perovskites are naturally very stable materials, and two, they have an oxygen vacancy. The skeletal formula of a perovskite is AbO3. A is typically an alkali earth or rare earth metal. B is a transition metal element, and then there's three oxygen molecules. Experiment, I tested three different compositions of perovskites with barium, lanthanum, and iron to see which one was the most stable and produced the most carbon monoxide and water output. In this year's continuation project, I continued to increase the yield of water and carbon monoxide while maintaining the structure of the perovskite with the aid of a support catalyst. Since carbon dioxide conversion is largely dependent on the composition of the material, supporting the perovskite structure through the looping could help to test RWGSCl on a larger scale and optimize next generation fuel conversion materials. Silicon dioxide is introduced in this experiment because it is considered to be one of the most excellent support catalysts in terms of its stability and ability to increase oxygen vacancies and therefore help in the formation of carbon monoxide. The first thing that I did was make the perovskites by adding different compositions of silicon dioxide, but leaving one of them as a pure sample with 0% silicon dioxide. Then I conducted the temperature programmed experimentation. For the TPR, I took a U-tube and I put the sample into it. I then put the entire thing into a furnace and flowed hydrogen and helium gas through the U-tube to make the oxygen vacancy. During this process, one oxygen molecule left the composition and formed water, H2O, with the hydrogen. That water was then collected and measured in the mass spectrometer. In the TPO experimentation, I did the same thing. Instead of this time, I let the sample cool until it hit 500 degrees Celsius, and then I flowed helium and carbon dioxide gas through the tube. And this carbon dioxide gas mimics the carbon dioxide that it would be taking in from the environment. The temperature program reduction experiments show what temperature is ideal for each sample to yield water. We see that the pure sample reached the mass spectrometry level of 18 at a lower temperature than the composite samples, which each required 600 degrees Celsius to create oxygen vacancies. But more water is produced, which can be attributed to more surface area of LBF exposed to gas interactions. The TPO results indicate the same, as the pure sample requires a lower temperature than the composite samples to peak and make carbon monoxide. The higher peak temperatures are related to the phenomenon of the formation of cationic vacancies during the sintering of LBF and silicon dioxide. This also shows the increase in oxygen vacancy energy as the vacancy in the lattice gets larger. To maintain electrical neutrality during the cation vacancy, one of the nearest metals acquires two positive charges. And in this case, it's the iron and lanthanum, and this causes a shift in the perovskite reduction temperature. The TPR profile suggests that 600 degrees Celsius is the adequate temperature for achieving numerous vacancies before carbon dioxide conversion while still retaining material intactness. These two processes are called RWGS-CL chemical looping. Looping results indicated that the LBF silicon dioxide 25% achieved the highest carbon monoxide and water yield. The pure form, or the 0% form, had the lowest production of water and carbon monoxide, and that could be because it lacked the silica support, which caused the material to decompose at a faster rate. An increase in oxygen vacancy is directly correlated with the amount of water made in the looping rate. The silicon dioxide helps in oxygen vacancy as the water yield increases significantly when it is added to the pure LBF. The LBF silicon dioxide 50% shows a lower yield of carbon monoxide and water, and this could be due to an increase in formation of iron silicon trioxide and lanthanum silicon trioxide at the LBF silicon dioxide interface. The secondary phases can reduce the composite's ability to accommodate oxygen vacancies and carbon monoxide generation capacity. But the LBF silicon dioxide 25% shows the maximum yield, demonstrating its minimal secondary phase formation and maximum wettability. The data table lists the production of water as much higher than the production of carbon monoxide for the 5 trials. And this could be because the entirety of the perovskite, surface oxygen, contributes to immense water formation during first-time reduction. But replenishment is not possible because of the gradual buildup of kinetic stagnation during carbon dioxide conversion. Also, the activity of oxygen vacancy sites during carbon monoxide formation is closely related to the net number of oxygen vacancies at any time. So this means that the higher the availability of oxygen vacancy sites, the higher the carbon dioxide absorption over a perovskite. But as carbon dioxide converts to carbon monoxide, the sites do not get replenished, which causes a gradual stagnation of surface exchange kinetics and results in less carbon monoxide production than water in the first cycle. Lastly, X-ray diffraction was used to evaluate the material stability, as changes in the crystalline structure would indicate low material stability and poor long-term endurance. By looking at the graph, we can observe that the structure of the material did not change after the TPO experimentation. The main peak in the graph shows the material can maintain its structure. The post-TPO graph shows the same peak as the fresh sample, which shows that the material did not crumple and decompose even after the heating, which means that the silica did help to support the perovskite structure. At the end, I determined that my hypothesis was correct because the 25% silica did help in producing the most water and carbon monoxide while still maintaining structural support and long-term endurance of the perovskite structure. If I were to conduct this experiment again next year, I would focus on the second phase of conversion, which is converting the carbon monoxide to hydrocarbons, which can be used as a cleaner fuel alternative and help to combat global warming.